gotta. So what did you get, Eric, for that percentage?
No, let's watch Graphman. Graphman is a math.
Yeah. And some of you might have remembered that like this does sound somewhat familiar or something. So, so it is true that we're going to talk about normal distribution. It's heartening to remember though that you guys, apparently you thought about the normal distribution a little bit before in Algebra 2, if you took the county curriculum. So that's good, and maybe you'll learn nothing today. That'd be good. Or maybe you need a refresher. I don't know. You think you need a little bit of a refresher? We're not going to do very much. In fact, actually, you did more with it.
1.568.5, and then there's like
Something like that. We'll get to that.
Never
And
have
then,
100% because
yeah.
it's infinite.
So properties of the normal distribution, you already mentioned one of them, and that's that it's symmetric. What other properties do we desire? Because it's not just good enough that it be symmetric. Obviously, there are lots of other curves that that are symmetric.
Those words are coming back.
Yeah, we want it to be single peaked, or unimodal is a great way to say it too. And then, of course, it's not good enough maybe to have it be single peaked. We also do require that it kind of have, like someone has said already, a bell shape to it, right? These are all non-examples up here, right? In fact, another way of saying a bell shape, if you wanted to like talk about function language, would be that it has these 2 points right here and here, which are called what? You know what those are called? For a graph. Where the concavity of the graph changes from being concave up to concave down, and then to concave up again. Maybe you've never seen that, but it curves. It's curving this way, and then it starts curving this way, and then it starts curving that way. You don't have a name for that? Maybe we haven't really discussed it that much this year. But you might call those inflection points on the graph. Is that a word you've heard before? I don't know. So the point is, like, the top two examples in the far corner are ones that don't have that kind of flare out, that inflection on the two places there. It turns out for a normal distribution that the mean and the standard deviation entirely determine a normal distribution. So if you're communicating to someone, you want to talk about a particular normally distributed random variable, then all you need to tell them is two things, the mean and the standard deviation. And a lot of times we just package them and write them in this notation right here. We say x is a random variable that's distributed with a normal distribution with mean, mu and standard deviation sigma. And that's all you need to say. Now, to be clear, that doesn't give you this picture though yet. How do you actually graph that picture on your calculator? If you were to like put that in y1, what equation would you enter in order to see this picture? And I'm not sure that you would have learned that in Algebra 2 last year. But I'll share it with you, even though it's not still something you need to know or memorize. But I'll show it to you anyway. You do not need to know this, but here it is. I'm going to shock you and surprise you. Okay. So this is the equation for the normal distribution. The standard normal distribution, I should say. This is not just any normal distribution, this is the standard normal distribution with mean 0 and standard deviation 1. Okay. And if you graph that in y1 on your calculator, you will get this picture. And if you ever need to know this equation, it's painted in red above the lockers over there. It's so important and useful that this is it. This is called the standard normal distribution. And from that equation, not even thinking about statistics, just thinking about algebra and functions, can you see that this function has the symmetry that we desire it to have? What kind of function is it? What kind of symmetry does it have? It looks complicated, but there's just a big constant in front of it. That's what yeah, and so that ensures that it has what kind of symmetry?
About the y-axis.
Yeah, across the y-axis, it's a what kind of function?
Even.
It's an even function, which is good. We want this to be symmetric, so that's great. What else is true? Well, what happens when you take the limit of this function as x tends toward infinity? What is the limit of this as x goes to infinity?
0.
Yeah, it approaches 0, right? Because if you put a million and you get e to like negative a million, and e to the negative a million is basically 0. What about negative a million? What's the limit as x approaches negative infinity? Also 0, and you can see that the x squared is ensuring that and is doing the job of making that limit happen in both cases. We have the x squared ensures that we kind of get that exponential decay on the right and on the left. So even though it looks very complicated, in the end, it's actually really kind of makes sense, a lot of the pieces of it, why we get a picture like this. Now, it still remains a mystery why the pi and the e are there. And that's pretty thrilling to even realize that those might be a part of this. But there is one other demand besides symmetry that we have for this, and that's that for every normal distribution we might encounter, that the area under this curve be 1, right? And ensuring for a function that the area underneath of it is something or some other thing is not under the purview of a pre-calculus class. So we're not going to discuss how to make sure the area of and under the curve is a certain amount right now and right here. But it would be the subject of the calculus. Subject of the calculus course. What was your question? Yeah, and again, you're not going to need to know this formula, and if you ever do need it on the wall. Or you just do that. Okay. No, it's okay. I mean, then this PowerPoint's available online as usual. Recorded. Yeah, points and inflection. Again, not something you have to. I just wanted to share that that's where those are. A translation occurs left and right if you change mu. I think that's to be expected. This kind of goes hand in hand with the stuff we talked about at the end of last unit. What happens when you change the mean or the standard deviation of a random variable? Like what happens to these things and what happens to the distribution? Well, yeah, changing the mean corresponds to a left-right move. Changing the standard deviation sigma corresponds to a spreading out or a shrinking, a tightening up of the data, right? So you can see in these pictures in the red, we have in the red solid line, we have the standard normal curve with mean 0 and standard deviation of 1 in solid red. And then you can see various modifications of that. In green, we've moved the mean to the left, and now it's at -2 instead. Yeah, and actually they didn't.
Variance.
They have the variance. Actually, the place I stole this from, I think it's from Wikipedia, has over here not reported the standard deviation, but the variance for each of those. But whatever, it's still a measure of the spread, so we're okay. But you can see for a higher standard deviation, we get a much more spread out curve in purple here. And for a very low standard deviation, we get a tight, high distribution. But in all cases, we have a normal distribution. They're still all normal distributions. And in all cases, the area underneath all of them is 1. Each one of those is 1. So, not a huge surprise there. I just wanted to show you that these do come in different shapes and sizes, even though they all still do have the properties we outlined earlier. Different things in the real world that you'll encounter. There are lots of them, but a couple different examples of things that might be distributed normally include the following. Things like test scores are often normally distributed. And also lots of measurements in biological populations, like the 3 ones that I've written down here. Right.
Yes. Just when I was doing my life.
And then even though that might sound very scintillating, that's very exciting that, oh wow, that's amazing. That some things are, why is it such a special distribution? Well, really the core principle is not that it just keeps coming up in nature, though it does. And these are related ideas actually. But also, and I won't say very much about this, but also for when you do take stat, it turns out there's like a very, very central idea to statistics called the central limit theorem, which shows you that the normal distribution is actually related to every other distribution, amazingly. And that's actually not hard to say, so I'll say it quickly. And that's that if you repeatedly sample from some crazy distribution, maybe it's a distribution of I don't know, shoe sizes or who knows what, you repeatedly pull from that distribution over and over again. You take samples and average those samples, and then you take another sample and take the average, take another sample and take the average, and then you plot the averages, you get a normal distribution, regardless of the distribution you pulled from. So that's a pretty like 30-second description of what the central limit theorem is. And if you'd like to know more, you'll take AP Stat. Have we done this before? Point two. Yeah, and actually, actually, you probably know this better than the people who took the sophomores I was talking to yesterday, who didn't have an Algebra 2 experience quite like you did. You actually did the county Algebra 2, which now has lots of like sampling distributions and all sorts of stuff like that. And so maybe you already tasted this a little bit. You already felt like this. You already heard that. So like when we sample and we like plot the sample means or whatever else, then you get a normal distribution.
Does the recording thing record us?
Yeah, of course.
Oh, okay.
Yeah, would you like to say hi, Mom? Go ahead.
Hi, Mom.
Yeah, it's just a mic up here.
Oh, hello, recording thing.
But how do you get the recording thing? Like, I want to try to do that.
Oh, it's Active Studio, but you can get it's Active Inspire or whatever. But you can it's not the only piece of software that does free recording.
I apologize. I'll bring the paper things that record me one day. Sorry about that. You're not today.
So let's now return to the rule that we looked at even as it was coming up in the warm-up, and you guys were like harkening back to that time when we were like remembering these percentages. Yeah, sometimes the rule, this empirical rule that I'm introducing right now, is remembered as the 68, 95, 99.7 rule. That might be the thing that you remember from your algebra 2 a little bit. I have them in slightly more precision in the slide that was listed here, and I have the full picture here as well. Right? Again, stolen from Wikipedia, I think. And like someone else was mentioning, I've divided this like kind of into slivers where we have a standard deviation away from the mean, right? And then another standard deviation away from the mean. And we already have this sense that like the standard deviation measures spread, but it also can be used as kind of a measuring stick. For your score on the test, you can see how weird your score was. So if there was like a 90% average, and I tell you that in the class average was 90, and the standard deviation for our class was like 5%, then and you got like 100 or you got an 80, not only have you shown that you're somewhat close to the mean, or you did well enough, but you've also said like how strange, how if you're like 2 standard deviations away from the mean, in some sense, like that measures like how out of the normal that is, right? That's a very abnormal. That's really a remarkable score. In either direction, it's equally unlikely that would have happened. So you're a very special person. Now you'd rather be maybe the 100 than the 80, but in both cases you're special, right? Yeah.
Have you ever broken this out whenever anybody asks you how do we define normal? Like, how can we define what is normal? And
I will leave that to you, Ian, and I know you will. Okay. So.
That I shall.
So you can see that maybe we want to care about like how many standard deviations we are away. By the time we're 3 standard deviations away from the mean, if you're working with a random variable that's distributed normally, you basically collected all the data within 3 standard deviations. There's very, very little that falls outside of 3 standard deviations. So much so that, like you said, hey, on the last test, I scored like 5 standard deviations away from the mean. I'd probably guess you were lying or making a mistake before I would like believe it. It's so unbelievable and so unlikely.
Didn't do the test.
All right, let's look at the head circumferences of Army people.
Is this true?
Ready? I don't think so. I don't know. I forget now where this comes from. I've had this in my repertoire. I stole it from some book somewhere, so maybe they have. I don't know. So it's important that we say this. The head circumference of these soldiers is approximately normal, with mean 22.8 inches and standard deviation 1.1 inches. And let's use this rule that we just developed, and I have a picture down here, to answer these 3 questions, and I'll just give you a minute to do that. Convenient numbers, aren't they? I just mean in my questions. You'll find them to be convenient numbers.
Oh, 25. You're right,
25 is a nice number, isn't it?
Yeah.
So, yeah, let's just say what that is then. Shine, did you figure that out? What for 21.7 to 23.9, what are we talking about there? Yeah, because I guess I said it was going to be that, and so you just trusted me. Good job. Those happen to be exactly one standard. That was really convenient. Those are exactly one standard deviation below and above the mean. And then what do you see on B, Amber?
It's the 95.4 percentile.
Okay, so, well, now careful. The percentile means something a little bit different than I think what you're thinking. What does percentile mean? It means the percent of scores that are below you.
So 95.4.
Well, that gives, I know this is confusing, but remember that's the percentage of observations that fall within 2 standard
So
deviations.
97.8.
It would
Is that right?
be 97.7.
Yeah, how'd you get it?
Oh,
I just added
sorry.
the 2.1 on the
Yeah,
point one,
6.
because I already have all the data within 13.6 and 3.
So other people want to confirm. Would you say it's 97 point?
Yeah, 0.6.
Yeah, 0.6.
0.6? And how are you getting that again?
Because
Oh,
you
from
know that within 2 standard deviations, you have 95.4% of the data. And then on the bottom half, you have to add 2.1 and 0.1. So that would be adding 2.2, which is 97.6.
all right, yeah, and the numbers on this are a little round. They're obviously rounded, so we might have some discrepancy. I see how you got that. Does someone have another number that you got using your method? Eventually, in a minute here, I'll show you an even more precise way to do this. But yeah.
Outside of the 95.4%, you have 4.6% of the data. Now, of that, considering it's a normal distribution, thus symmetrical, 2.3% will be below the given data distribution, thus giving you a total of 97.7%.
Yeah, I think 97.7% is also what you get if you add these up. But it's weird because obviously then you become short on the data. In fact, if you add these up, you get 2.2. So maybe it's 97.8. I don't know.
That's because it just sort of goes on into infinity.
Well, we're like rounding. All these are rounded, right? So that's the issue here, right? So we can eyeball this. Whatever you said here, what should the answer be here? How are you getting the next answer? Anyone? Yeah, it's the other part you didn't calculate, right? So what is it? So if you're this person,
2.3
you
or
might say 2.3% or something.
2.4.
And like I said, that lacks a little bit of precision in our mind maybe, but we're getting the right idea. Okay. So then the next question is, well, I have a couple follow-up questions. One follow-up question would be just for fun, and I don't really want to answer it right now, but what about that? What's the probability that someone's head circumference is 25? We're just talking about what's the probability that you have a head circumference less than 25. A probability that's greater than 25. What about probability that equals exactly 25? That's an interesting question. I don't know.
There's no way to tell.
Find the height that is definitely.
Find the height.
Wait, there's no way to
That
tell.
thing with draw the line.
Oh.
Okay.
I mean, that's an interesting question. What's the area? I guess the point too we could ask is like, what's the area under the curve there, right? Isn't that really what we want to do under that one point?
Yeah.
Yeah, I guess.
It's not the height though,
Oh, it's not.
because it would be the height times the width, wouldn't it? Be?
How much is the width of a point?
What is the width of a point?
Nothing.
There's no point.
Yeah, the probability that your head circumference is exactly 25 is 0, right? So, you know, what's the probability that your head circumference is like 25.00000000000? Is that what you really meant? It's like, what's the probability that your head circumference is exactly 25.000000000? 0, right? There's no.
At some point in time.
You probably had some tolerance when you measured it. Now, would you like, maybe what you really meant is like, what's the probability that your head circumference is between 24.95 and 25.05? Now that's a non-zero probability, right?
But
But
isn't there still always
it's
a chance that
vanishingly small. I know it's unsettling, but for any given, I mean, now you have to think about this too, right? Like what's the length of the interval 0 to 1? Well, it's 1, you say. Well, what if we remove 1 point? Is it still 1?
Just one problem with that theory of logic, though. At that point, it means you could have never been exactly 4 feet tall if you're 5 feet tall now. You could have never been exactly 4
Yeah,
feet
we
tall.
now need
But
all of us
that's
to
not
take
how it works.
take a course in measure
Wait,
theory or
wouldn't that
something.
mean that no one anywhere has
Concept
a sizable
physicists.
head?
Of any
No.
kind, I know. Nothing is likely at all, exactly.
That means everything is
This
false.
is like very, very deep. So, to be clear, we won't really ask you this. Okay?
Thank you.
But I just want you to like think about it for a second. So if someone says, what's the probability that my head circumference is 25, is less than 25%, it's 97.7%. But if someone said it's like, what's the probability that my head circumference is 25 or less, it's still the same, right? We treat those as being the same inequalities. For a continuous random variable, this discussion arises, right? Now the other interesting question here too is, what about z-score? I gave you really nice values. What if I give you a not nice value, like 23.35? You do have to like think about it. Well, I don't know. I guess even for 25, how did you figure out that that was 2 standard deviations? Well, I mean, some of you did it so immediately in your head that you don't have
Well,
a
you
set
subtract
of
it with the
reasoning.
mean and then you multiply.
No, you subtract the mean.
Yeah,
Oh, yeah,
you found like that distance. You were like,
Yeah.
okay, well, 25 is like 2.2 away, and then you said, well, that's
Divided by the standard deviation.
well, then you said divided by the standard deviation gives you 2, and you did that so immediately in your head that you didn't really think about that as being like a formula you were using. You were just like, I'm kind of like measuring with the measuring rod of standard deviations. I find the distance and I divide by the number of what the standard deviation is, and I get the number of standard deviations I got, and that comes out to be 2, right? What does this one come out to be? I don't know. How many standard deviations is this away from the mean?
Oh, Eric is it's 1.5 and 1.1. So, oh, it's 1/2. It's half the.
Yeah, this is 1/2 of a standard deviation above the mean. Is that okay? Yeah, it is. I don't have a place for that on my chart, but it's certainly fine, and it still quantifies like how weird your head is, right?
Wait, could you
Exists
just
somewhere.
divide?
Oh wait, no, it does exist because it's a single point thus has no width.
So this measure of standard deviations, the measure of weirdness, this measuring rod is sometimes called the z-score of your piece of data. And I hope before you see this formula that you already like kind of admit that you don't need it, right? We just talked about how to do this, and that's what we were just doing, right? So the z-score is that value. And notice that sometimes it comes out to be negative as well, right? And that's a desirable property, because then that tells you not just how weird you are, but in the direction of which direction you're weird.
Mr. Chase, which direction are you weird?
I'm
No comment.
depends on which scale we're talking about, right? Which measure are we using?
Head circumference.
Oh, for head circumference? I don't know. I think I'm average on that. I think I fall in the middle for that. I'm eccentric in other ways, but maybe not in my head size. All right, so go ahead and find the z-score for each of these 3 song lengths for this album that has assume a normal distribution, and we got a mean and a standard deviation.
1.08. Do I have those right?
Let's let everyone work on them real quick.
Yeah, but
What's that?
if points have no length width or any dimensions of any type, then how can they make up anything?
Right. This is a very
Therefore, why?
thorny
therefore-
paradox.
But then that means that your graph is made up of an infinite number of nothings. Therefore, your graph is nothing.
We'll discuss this later. I have a lot to say about this here, but we'll talk later. Okay.
Now, how much
I opened. It's my fault. I opened up. I asked you what the probability of x equals 25 is. So, but we'll talk more later. I have a lot to say about this. And so do mathematicians at large. You should take a course in real analysis and then also a course in measure theory. There's like a whole course you could take with this as its topic. All right, let's just get these answers then.
Probability of everything is thus 0.
How about Annabelle, the first one? What did you get there?
4 minus 3.05
Well,
over
that's true. Well, good job. Yep. Can't lie. That's right.
That's the right answer, Mr. Chase. Okay, 1.08.
1.08.
Yes.
Agreed. Eric, what'd you get for B?
Wait, I'm just confused myself.
Uh-oh. We'll come back to you in a second. He's going to do B. And Ian, you want to get C?
2.22 approximately.
2.22,
When around
somewhere
pretty
confirmed.
significant figures.
2.22. Okay. And Eric, what'd you get for the middle one there, B? Yeah, it'll be negative something, right? Yes?
Negative 0.627.
Is that what you got?
Come on.
We'll let up on it, don't worry.
Negative
Zero-
0.626.
All right, now the thing you might be concerned is not just like how weird a song is, right? How many standard deviations it is, but we'd also like to, even if it doesn't fall on one of those nice boundaries, we'd still like to calculate the probability somehow, right? Now, if you took that algebra 2 course that we were talking about last year from the county, you used maybe a table to compute some of these, or maybe they showed you this function on the calculator, but let's use this function on the calculator called normal CDF. It's located in the same place that you find binomial CDF. CDF under second bar, the distribution menu. And let's just verify that it works. Here we go. Let's find the probability that a z-score lies between negative and positive 1. Now you already know the answer to this. What's the answer going to be? If your calculator is working correctly, it should give you what as the answer? Sorry. Let's actually, yeah, what should it give you based on our discussion already? Yeah, it should give you 68.2%. So type in -1, 1. That normal to CDF, comma -1, -1, 1.
Wait, how do you find A and B? Oh, are those the
And it
standard deviations?
should give you the same thing we said earlier in this lesson, right?
What are A and B?
A and B are the left and right endpoints of where you want to calculate the area. So here's A,
Standard deviations of the
and here's B, yeah. And then what's this probability even without the calculator? For each of these, I'd like you in the homework to shade too, to draw a quick sketch of the normal distribution and shade. So what should that be, even without the calculator? Good. Now we need this on the calculator. So we're here. 1.23 is like up there, and we're looking for that area. So on this one, this is actually a little bit trickier, even though it looks maybe like it would be easier. It's actually a little trickier. You have to say what 1.23 is the left endpoint, but then like positive infinity is the right endpoint. So
1.99.
yeah, just use something large. And you already know that like 1,000 is very large because 4 is, right? Like even 4 standard deviations is like so far out that like there's almost no data there. So if you want to be safe, 100 is fine, 1,000 is super fine, and you won't see.
1.99
So,
is effectively you're not getting it wrong.
yeah, try that. What did you get there?
10.9% or
10.9.
0.109 per decimal.
0.109. Okay, and I don't care. You can report it as a percentage too. Yeah. Oh, these are optional. So these are optional. If you're doing this later, and we'll do some more of this on Monday too. If you have things that aren't z-scores, then and they're on some mean standard deviation. Right now, the command you're entering is 1.23, 1,000. Without even saying it, it assumes 0, 1 is what it assumes.
Wait, so that's for a normal distribution?
If it's not a standard normal distribution, you can put in the mean and standard deviation. Yeah.
My calculator has a thing for upper bound and lower bound, and so I
That's
can
exactly
do that
right.
on
Yeah.
A, but then how do you do that on B?
This is lower
No,
bound,
no,
this is
no.
upper bound.
The, like, letter B? Like,
Yeah,
the
exactly. So you do
probability
0 for the lower bound.
And for the upper bound, just put like 7 quadrillion.
Yeah, put in 1,000 again for the upper bound, just like we did here.
I like 7 quadrillion
Oh,
better.
well, once you get like a different
No.
number.
Try 1,000, try 10,000, and see that you get basically the same thing to 9 decimal places. That really, it's sufficiently large, yeah. You don't need to on those. Those are all z-scores, right? So the mean and the standard deviation. The calculator just assumes the mean and standard deviation is 0 and 1, unless you specify otherwise. You don't have to enter those. You can always enter them if you want to. If you want to do the reverse, you can do a lookup. You can do inverse norm of 0.63, and that will give you the z-score to the left of which 63% of the area lies. Right? So what is this z-score? Well, when you type this into your calculator in a second, you're going to know. I think it's 0.332.
0.33125.
What is it? 0.3 something?
0.332 when I
Yeah. 0.332 is the z-score. So, like I said, a quick crash course in like everything you learned from Algebra 2 last year. There you go.
So,
Your calculator's handy, right? You like that? You like the calculator?
It would be nice if I had it.
The homework says homework 4,
Murad, please come to the main
it's the
office.
one you're supposed to do.
Edith,
Okay.
Murad, please come to the main office.
Okay, and Alex,
Just how come you always wait until the now has gone to give us our homework?
sorry.